Alright, so we're going to introduce two things. One is, both are new, the radian measure and how that relates to degrees, and we're going to finally build our first unit circle, which really expands our definitions of trigonometry into our full circular function definition. So we start with the circle, and as described before, it's called a unit circle because if I take my radius, it's a length of 1, and I have some coordinates x and y. I go over x and up y, and that's going to give me points on that circle. So we're going to define a couple of terms before we get into the full-blown unit circle. So we have angles, central angles from the circle that are measured in something called standard position. And standard position starts at the origin and goes along the x-axis here, and then to rotate, we define a counterclockwise direction as a positive angle. So I would start along the x-axis and I rotate some angle counterclockwise. That is a positive standard position angle. So if I went up 45 degrees, I would start at there and I go up 45 degrees, and that would be a standard angle of 45 degrees. Now if I did negative 45 degrees, I start at the same spot, but I go clockwise from that direction. So most of our angles are going to be this standard position. That's how we define most of what we're going to do here. Alright. We're going to introduce another way to think about an angle, and that's primarily as an arc length. Alright, and an arc length we're going to define as x. So we're going to relate the two using a proportion involving the central angle and the circumference. So I have theta over 360 degrees is the arc length over c, where c is the circumference. Now, our formula for circumference is 2 pi r. Well, since our radius is equal to 1, that means that I can take out the r and put in a 1, and I get theta over 360 is x over 2 pi. That's going to allow us to relate an arc length to an angle. And that arc length is going to be something called a radian measure. And you can see if we were to get theta equals something, we would have 180 over pi times equals x. And so that 180 is an important spot to look at. 180 degrees, well, that is halfway around the circle. And if all the way around the circle is 2 pi, halfway around in radians is going to be pi radians. If we solve it, it looks like this. 1/2 of 2 pi, pi equals x. So that is going to be 180 degrees is pi radians. That allows us to go back and forth. It's an easy conversion factor for converting radians and degrees. Alright, we also have something called coterminal angles. Coterminal angles are angles that end in the same spot but have a different measure. So you can see here I have some endpoint, x, y, and I can go theta, which is the red angle, or I could go theta plus 360 degrees and get a coterminal angle. That's an angle that ends in the same spot. And that's going to be important as we expand our definitions of sine and cosine to involve these coordinates. So these coordinates are going to become very important for how the unit circle is constructed. Alright. We have one more thing to really talk about, and that's a reference angle. So our sine, cosine, and tangent ratios are defined for a right triangle. But if I'm over in quadrant 2, I am already bigger than 90 degrees, and I can't draw a right triangle with an angle that's bigger than 90 degrees. So what we define is if I have some angle, I have a reference angle, or theta ref, which is the acute angle formed by the terminal side of our angle and the x-axis. So it'll always be to the x-axis, it will always be acute. And something we're going to want to keep track of is if I'm over in the first quadrant, I have positive coordinates. Over here I have a negative x coordinate. Down here I have a negative x coordinate, negative y coordinate. And over here in the fourth quadrant I have a positive x coordinate and a negative y coordinate. Those will be important for sine, cosine, and tangent as we go through this. Alright, so we're going to start building our unit circle. And it's going to look like this, and it's been divided up into certain measurements. Now, a unit circle means we have a radius of 1, so I go out 1 and up 0. Another easy point to get is 0, 1. I go back 1 and up 0, and then I go down 1 and over 0. So I get those 4 corner points. Those are going to be important as we get into graphs of these functions, but for now we're just going to label those points and go through it. Alright, so I am going to label my degrees here. I have a 0 degrees, that is 30 degrees, that is 60 degrees. That's 90 degrees, 120, 150, 180. So all I'm doing is adding multiples of 30 degrees here. 210, 240, 270, 300, and 330 degrees. So those are all 30 or 60 degree reference angles. So again, as if I was to look at the 330, the reference angle is 30 because that's what it makes with the x-axis. Over here at 240, the reference angle is 60. So why is that nice? Well, what I'm really going to construct here is a 30, 60, 90. We know a lot of stuff about 30, 60, 90 triangles, but we also know a 45, 45, 90 triangle. So I'm going to put in my 45 degrees as well. At 45 degrees and then 90 degrees, I'm in the same spot. 135 degrees, 180 degrees, 225, 270 is the same spot, 315, and then 360 gets me back to the front. So what we've really done is we put on angle measures so that when we take a reference angle, we're going to get a 30, 60, 90 and a 45, 45, 90 triangle. So here's our first one. I have a 30, 60, 90 triangle where my hypotenuse is 1, right? And I solve for my missing pieces. The side opposite 30 is 1/2. That side is root 3 over 2. So I label those coordinates, root 3 over 2 and 1/2. Now, if I take sine of 30 degrees, that's the opposite over the hypotenuse, and since the hypotenuse is 1, it's just going to be the opposite, or this coordinate here. If I take cosine, which is the adjacent over the hypotenuse is 1, so it's just this value here. So this is a key shift. We're going to find that our x value is cosine, and our y value is our sine value of those angles. So let's draw our next special right triangle, which is the 45, 45, 90. If we solve it with a hypotenuse of 1, we get x root 2 equals 1. We solve for x as 1 over root 2, and we rationalize that to get root 2 over 2. So that coordinate is root 2 over 2, comma root 2 over 2. Now my last one is the purple triangle, and what we notice is it's a 60-30 triangle, and we've already solved that once, so my pieces are just going to flip around. I get 1/2 and root 3 over 2. So my coordinates for the first quadrant are 0, 1, for my point here, root 3 over 2, 1/2, root 2 over 2, 2 over 2, 1/2, root 3 over 2, and then 0, 1. If I know this backwards and forwards and where it comes from, I can get the whole circle really easily. And the way that I do that is I just use some symmetry. So this point over here is the same y value, same point up, but the x value has become negative. If I draw that triangle, it looks like this. So my coordinates I know are going to be a negative root 3 over 2 and a 1/2. And this is where we leap from being an acute angle for our trigonometry, which is in quadrant 1, and now we're over in quadrant 2, where I have an obtuse angle of 150 degrees. And so if I plug in my calculator cosine of 150 degrees, I should get negative root 3 over 2. The root 3 over 2, I obviously don't have a negative distance, but I talk about that as a direction. And so we are going away from just being a purely right triangle idea to an obtuse angle, and in fact, angles that are bigger than 180 degrees. So that's where we're going. If I reflect the green triangle, it becomes negative root 2 over 2, root 2 over 2. If I reflect the purple triangle, it becomes negative 1/2 and then root 3 over 2. I can get the other points by symmetry as well. So if I flip down that red triangle, I would have a negative x and a negative y value. If I flip down the green triangle, I have a negative x and negative y value. If I flip down the purple triangle, I have a negative x and negative y. Now I'm over in quadrant 4. So if I bring the purple triangle down, so if I take this and I come straight down, it's the same x value, but the y value has become negative. So it's 1/2 negative root 3 over 2. My green one is positive x value, negative y, so root 2 over 2, and then negative root 2 over 2. And the last one is root 3 over 2, negative 1/2. So in the first quadrant, everything is positive. Over here, x is negative. Here, everything is negative. And then over here, I have a negative y value. And we'll get an acronym down the road to remember those. All right, so that's our big idea, but we haven't put a key component on it, and that is our radian measure. So if we labeled our degrees, we are going to see that 0 degrees is 0 radians. It's an arc length of nothing. If all the way around is 2 pi, because my radius is 1, halfway around is pi from before. So 180 degrees is pi radians. This is half of the half, or pi over 2, and this part here is half of the half, which is pi over 4. All right, so I can see that these values are my pi over 4 values. And so I'm going to label those as we go through it. So that becomes 3 pi over 4, and then pi is 4 pi over 4, which reduces to just pi. This piece here is pi over 6, and we can look at it differently. Now I label all of these, and I did that quickly, but this is pi over 6, 2 pi over 6, which reduces to pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, which is 2 pi over 3, 5 pi over 6, and 6 pi over 6. So I'm counting by pi over 6, or 30 degrees, if that's easier to think about. And we can see where it comes from. I just take my proportion. 30 over 360 is x over 2 pi, where 2 pi is the circumference, and you get pi over 6 is my value there. All right, so let's put in the rest of our measures. We're just using our fact of things being proportional, so those are degrees as we did before. And then I'm going to count the rest of my pi over 6's. So again, this was 6 pi over 6, 7 pi over 6, 8 pi over 6 reduces, 9 pi over 6 is going to reduce, 10 pi over 6, 11 pi over 6, 12 pi over 6, which is also 2 pi or 0. It's the same rotation, same end result. All right. Now we need to put on the rest of the pi over 4. So if I look at it, we start here, 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, which is again 2 pi or 0 degrees. Those are coterminal angles. And now we put our coordinates back on that we had before. So those are from before. We have the 30, 60, 90, the 45, 45, 90, and then the 30, 60, 90 flipped around. And now that we have that, we can label everything by just using the fact of x and y being positive and negative in different quadrants. So if we do that, there's our triangle, right? If we can't remember what's happening here, we really just have pi over 3, which is 60 degrees, and we're solving things as we had before with our 30, 60, 90. So we have to know the 30, 60, 90 backwards and forwards. All right. And if we take sine of pi over 3, since our hypotenuse is 1, it just gives us our y value, our coordinate. Cosine of pi over 3 is over 1, 1/2 over 1, which is just 1/2. So the key idea here is that on the unit circle, my x value is my cosine value. My y value is my sine value. So we can just, if I know the coordinates and I know the angle, I can figure out sine and cosine exactly for angles larger than 90 degrees. So if we put the rest of the unit circle on, we're just using the symmetry of it. We're just making things positive and negative as appropriate. So we get all of our labels there, all the way around. And we have completed our unit circle. Again, if I wanted to know cosine of 7 pi over 6, I find 7 pi over 6. It's right here. Cosine is the x value. It's negative root 3 over 2. Sine of 7 pi over 6 is negative 1/2. Let's say I want to know cosine of 300. That's 1/2. Sine of 300 degrees is negative root 3 over 2. That's equivalent to 5 pi over 3, which is just the arc length as we go around there. And we could find that being using a proportion with our unit circle. Keep working on it. Draw it out. It'll start to make sense.